Hello and welcome to Quantitative Reasoning for Ecosystem Science, ESS 330, the Spring 2021 edition. I am Dr. Lefsky. I will be your instructor this semester. Who am I? I'm a professor in the Department of Ecosystem Science and Sustainability, where my work is in the field of remote sensing. Specifically, most of my work is in the area of LiDAR remote sensing. So LiDAR is a technology that allows us to map surface elevations and also the height of objects on the surface. So in the upper middle there's an image from the Tapajós National Forest in Brazil. And what you can see is individual tree crowns shaded by their height using color. On the upper right, there's actually a laser scan of an individual tree that was done by a student of mine here in Fort Collins. And on the bottom left is a map product I developed showing the height of forests globally as the first one of its kind. And I've worked primarily with NASA on their satellite missions, ISAT and ISAT-2. These were both sensors that were developed from measuring the topography of ice sheets that I then subsequently used to map tree height. You've got two great TAs this semester. Josh, who's a graduate student in watershed science, which is a field with a great deal of quantitative content, so he's going to be really great for that. He is got 16 years of GIS experience and has worked at the Geospatial Centroid, and has just a really nice background. I'm sure you'll get along quite well. And Amanda, who is currently a PhD student in ESS, and she is interested in tropical forest science. So she's from Brazil and has worked in tropical forests with Daniela Cusack, one of the professors in our department. And office hours, I missed those for Josh, but are on these slides. They are also in the syllabus along with all of the contact information. The syllabus is posted on Canvas. There's a schedule there. Let's face it, it's crazy time, and things may change as we move forward. So what are we going to do? Primarily, we're going to be looking at an ecosystem and ecological analyses that use models and data. We're going to be looking at, using your critical thinking skills and specifically how we represent data and systems quantitatively. Okay, so ultimately, to have the best confidence on what we deem sustainable or what sustainable management strategies are, we would like to have data that will allow us to evaluate various different policies or potential actions. So in order to understand how ecosystems work, we need to bring data together, and then in general we need models as well, models that tell us how the various parts of an ecosystem interact and affect each other. And so this course is all about how to use quantitative information to both judge the validity of hypotheses and to develop models concerning ecosystem structure, function, and sustainable management. And our objective is to challenge you to think critically using data so you can inform your answers to questions and develop better understanding about how ecosystems work. The course is going to consist of 50-minute lectures, approximately. delivered asynchronously via YouTube, and I'll show you where you can get um, how to easily access the YouTube lectures. And there's also 1 2-hour lab period per week, and those will be conducted via Zoom. Most of the labs involve the use of a computer and software used to either develop models or to plot, explore, graph, and analyze data. This software, some of which you might have on your own machines, but which all of it can be accessed via remote desktop. So if you, that is via remote desktop using the WCNR PC lab. So if you have not used remote desktop to access the PC labs, then I would advise that you take this opportunity to figure that out. And you can just go to the IT webpage. It's, Warner CNR, College State EDU/IT, and they will give information. I will also include a link to an introduction that was done by a TA actually for another course, but that people seem to like. And there's no text. So here is our preliminary course schedule. So this is the week of January 18th. And so we're going to talk about just the introductory material, and then what is quantitative analysis. And there's no lab this week. I mean, this is actually going on Friday, so you already know that. Next week, there will be a lecture up by Monday morning on data and evidence. And there will be a lab next week. It's actually a group thought experiment on graph interpretation, seeing how much information you can get out of particular graphs. Grading, there will be 3 midterm examinations. So there will not be a final. There will be instead a midterm on the last day of the course. Lab assignments, there will be 8, and that'll be 40% of your grade. So keep that in mind. And then homework or exercises, there's going to be 4, and each one is 5%. Student expectations. We're gonna talk about understanding data from the collection of the data and the errors that are associated with that, all the way through your interpretation. Understanding hypothesis testing and multiple working hypotheses. Being able to think critically, deductively, and inductively, and we'll talk about what that is. Understand how we gain insight from data. Understand and incorporate into your thinking the uncertainty that we have for various measurements. Be able to use data to estimate parameters, so model parameters, and make forecasts using simple models of ecosystem processes. Understand a bit about the integration of economics into data models and decisions. Of course, in sustainability, economics is often a huge part of it, so it's important to understand. And then be able to interpret and evaluate arguments based on quantitative analysis data using models and commonly used statistical techniques. And finally, understand the space and time domains of models and data. So, whether if you're measuring soil moisture for, every second for 3 weeks, you probably don't want to use that information to interpolate or extrapolate, I should say, soil moisture information that might vary over, years or hundreds of years. And so depending on, how long you measure, how often you measure, and then, so that would be in time, over what time period, how often in that time period, and then over what extent you're measuring spatially, and then at what resolution, what's the finest measurement that you're making. That's going to affect how you can interpret your data properly. We're going to do a pre-course survey and a post-course survey. The surveys are not graded, but I do need everyone to answer. So please, if you can go to Canvas before like Wednesday of next week and fill out the quiz that's there, that would be very helpful. And that gives us a sense of what you've done before and what you haven't. And it's relatively quick. You just need to answer, A, B, C, D, E for each one of those 20 topics. So what is quantitative reasoning? Well, the basis of science has been that we resolve questions about how systems operate using observations. Now that may seem pretty obvious, but it's not necessarily. In other fields, the way that people have resolved questions about how things work or what things were is to argue about them, essentially. And of course, in many cases, those arguments can go on without being able to be resolved because the arguments are not structured in such a way that a simple observation can allow us to distinguish between one perspective and another. And so, it may seem very, very simple-minded and obvious, but in fact, that's the insight that propels science forward, is that we develop hypotheses that can be tested using observations so that we can distinguish between hypotheses and move forward in generating theory. So maybe you've collected some data, maybe you've read a paper on some experiment that describes data. And, in general, math is used in the sciences, whether it's equations or mathematical models, statistical descriptions of data, or hypothesis testing. And, ultimately under that data, there are, numbers or fractions or rates, graphs you may see, and descriptive statistics, all of which make up the evidence for a particular hypothesis. And quantitative reasoning is just the ability to apply mathematics and statistics in the context of real life situations and scientific problems. 3 components to quantitative reasoning: quantitative literacy, quantitative interpretation, and quantitative modeling. So quantitative literacy, understanding the mathematical methods used to interpret models. So the ability to perform computations, to compare between different sets of information, and estimating statistics of interest for groups of data. So numeracy is number sense, right? A sense for what are large values, what are small values, what are meaningful differences in what you're measuring, and what aren't meaningful differences. Scientific notation you should know by now, and logic, understanding basic logical, how to combine statements to make new statements that are logically following from your original information. And then measurement is an important part of quantitative literacy. Understanding the accuracy of your measurements. So how far are they from a reasonable, how far is a particular measurement likely to be relative to the correct measurement? What's the spread of repeated measurements? So that's precision. And understanding that in most cases, what we call measurement is really estimation, right? That there's always going to be some error associated with our measurement. And then understanding the proper units and how to combine those units, all parts of quantitative literacy. And then understanding rates and fractions and proportions, and understanding probability and statistics. So just empirical probability, the central tendency of observations, the variation of observations, and importantly, as we'll work on, understanding the probability and statistical concepts that apply to data sets where you have more than one observation, multivariate statistics. So next part of quantitative reasoning, quantitative interpretation. So looking at relationships between variables and exploring trends and making predictions. So looking at cause and effect, looking how the rates of change and relationships between variables can be described using algebra and statistics and calculus. The representation of quantitative information, so putting your data into tables, graphs, developing equations to relate variables, and their statistical display. And then developing science diagrams, helping users interpret complex or simple systems using figures. And finally, statistics and probability. So notions of randomness, of normal and non-normal distributions, correlations, confidence indices, confidence intervals, etc. And then the use of logarithmic scales and interpreting data plotted on logarithmic scales, or as logarithmically transformed variables. And then finally, quantitative modeling. So here we're talking, about building models that relate, say, a single variable to time or a single variable to other variables. So this is, formulating a problem, involving relating one variable to another, developing models, whether that's a statistical model or a systems model, as we'll talk about. Again, problem formulation and solving for models, and then regression models, so logistic growth models, multivariate models. Those would all be statistical modeling approaches, and then system simulation, which we'll get into as we go through the course. And then inference, hypothesis testing, looking at practical significance, and understanding the limitations of your results. Okay, so we've talked a bit about quantitative reasoning. The next lecture, the first quote-unquote real lecture, will be uploaded for listening on Monday, which is what, the 25th? Yes. And you will have lab at your scheduled time next